In recent years, pretty much every device has become a communication device. We're no longer talking about just handsets, headsets, and speakerphones, but anything that can transmit a call. This includes headphones, hearables, smart glasses, watches, smart speakers, and intercom systems, two-way radios, and more. Telephone standards that were exclusively applied to devices clearly labeled telephones are now applicable to all kinds of consumer electronics and are much more widely used than they used to be. Although it's not always required to test these devices to telecom standards, it's very worthwhile to make these measurements from a product performance perspective. You can easily measure things like double talk, voice quality, and performance to TIA, ETSI, and other standards using SoundCheck, which you may already be using for other electroacoustic measurements. In this seminar, we're going to demonstrate several communications tests that you can implement in SoundCheck on all types of devices. We'll start with the Telecom Industry Association TIA 920B that covers measurements for handsets, headsets, and speakerphones. We'll also show TIA 5050, which measures receive volume control performance, double talk for measuring echo cancelers, and Polka, a perceptual measurement of speech transmission quality. Good standards involve collaboration between many experts, usually from several manufacturers and test and measurement companies. This leads to useful and practical methods that can be successfully implemented with a variety of different tools. The development of the Polka algorithm was also a collaboration between multiple organizations. I've participated in many standards committees over the years, as has John Barham, who you'll hear from in a moment. He's actually head of the IEEE Telecom Standards Committee. Because so much consideration and effort goes into developing these standards, they are well thought out and a great place to start with testing devices. So what's the value in making measurements of all these different consumer electronic devices to communication standards? There are a couple of reasons. First and foremost, it's about designing a better product. If people are going to use their smart glasses to make phone calls, you want to make sure the sound quality is good so they don't remove their glasses and go back to their mobile phone. I can tell you from what I've seen with our customers that most successful consumer electronic companies take this kind of product quality very seriously. Secondary to that is preparation for external testing. At some point in your product's development cycle, you're likely to need to test for communications or voice control compliance. Many people use external test labs for this because a certified setup is so expensive. However, you can significantly increase the chances of passing certification by doing your own internal testing first. This lets you fix any issues before investing a lot of time, money, and effort in external certification. Okay, so let's move on to some demonstrations. With me co-presenting the seminar is my colleague Les Quindapan. Most of you already know him. Also with me is communications expert John Barham. Many of you might already know John, but for those that don't, a brief introduction. I've known John for well over 30 years since I worked with him at Brolin Care. Since 1991, he's been an independent consultant in electroacoustic measurements, specializing in communications testing, and his practical experience is second to none. He's measured communication devices, headphones, loudspeakers, microphones, hearing aids, hydrophones, sound systems, listening rooms, and probably a whole lot more. He also made many contributions to various communication standards over the past 3 decades. John's a longtime SoundCheck user and has worked closely with us since our early days. He has always been a power user of our software, and I think it's fair to say that John's communications testing sequences are probably some of the most complex ever written in SoundCheck. They use much of its functionality, and earlier this year, we even had to add some new features that he needed specifically for these tests. So that brings us to John's sequences. John has authored the TIA 920, TIA 5050, and Doubletalk sequences we're about to show you, as well as many others. These sequences take months to write and keep updated. So using these pre-written sequences saves many, many hours of development time, not to mention the confidence that you are correctly measuring to the standards. So let's get started with the demos. We have 4 demonstrations for you today: TIA 920B, TIA 5050, Doubletalk, and Polka. TIA 920 is a good place to start. You can use these measurements first for an overall check of critical functionality. TIA 5050 is a specialized test for mobile phone receiving performance. Doubletalk is a specialized test for performance of echo cancelers used for full duplex communications. And Polka gives a good estimate of how users would rate the overall speech quality. We'll start with a demonstration of some TIA 920 sequences. John's TIA 920 package is a very comprehensive set of sequences for send and receive response, level, distortion, echo, and more. John will tell you a little about the overall package, then run through demos of a few of the specific speakerphone measurements to give you a feel for what the sequences look like when they are implemented in SoundCheck. We only have time in the seminar to show just a small section of the total package, but we have a more extensive video on our YouTube channel if you want to see more of the sequences in action. Over to you, John.
We'll be showing you the SoundCheck sequences that implement TIA standard 920B. I'm John Baer, I'm developer of those sequences. I'd like to tell you a little bit about them and show you how they work, but first I'd like to say a little bit about the standard 920B. It applies to handsets, headsets, and speakerphones, and makes use of either hats or a mouth simulator and various microphones. It's comprehensive enough that it applies to almost any communication device. The sequences themselves implement the clauses in the standard. They cover almost all the important performance aspects of the phone. This is a typical setup for testing speakerphones according to TIA 920B. In this case, the lip ring of the mouth is 50 centimeters from the device under test, and on the other side, the microphone grid is also 50 centimeters from the device under test. In this view, you see the speakerphone oriented towards the mouth, and this is the arrangement for sending measurements. When it's time to do receive measurements, we can turn the speakerphone 180 degrees and point it towards the microphone to do the receive measurements. This is a very typical setup for a moderate-sized speakerphone. Different devices might require different setups, but this is typical, and if you're not sure where to start, this would be a good place.
So that's the setup. Thanks, John. Now we're going to demonstrate some of the measurements from this sequence package. As I said before, we don't have time to demonstrate all the test sequences, so we've picked a few specific ones that we think will give you a good feel for how they measure these important characteristics. These sequences are all set up so that you can save your data to Excel or to a master report that contains all the measurements you made. First up, we're going to measure receive frequency response and level.
When the measurement starts, we get a verification of the bandwidth of our measurement. If it's okay, we can go ahead. And now here is a reminder about the position of the free field microphone. Also about the device volume control put to nominal setting. If we don't know what that is, we can find that out from the measurement and repeat. The signal you're hearing now is a 4-sentence segment of IEEE male speech. It's used to condition the device into a stable state. The repetition of those 4 sentences is actually used for the measurement.
The ship was torn apart on the sharp reef.
The measurement didn't pass. The level is okay, but the frequency response is not. If you look at the upper left-hand graph, you can see a solid line that is the measurement in third octaves. It does not pass the mask. For information, there's a dotted line showing 12th octave measurement. And because they go together closely, that shows us there's not too many reflections in the room where we did the test. In the lower right is the waveform that was used for conditioning. That looks good. And in the lower left, the waveform that was looked for the measurement. That also looks good. So this appears to be a valid measurement, and now we will save the data. We could simply save the parameters in a simple Excel sheet, but instead we're going to put the data into a speakerphone master report that is formatted in a very nice way. We can add a word to the name of the file, could be whatever we type here, but we can also add comments that will go into the test report itself. It could be something about the test conditions, the volume control setting, or maybe something special. After some interaction with Excel, writing the data to the master report. The sequence is now finished.
There are also sequences for other received measurements such as volume control and also corresponding send measurements. They are all quite similar in format, so we won't show them now. Next, we'll show you a speakerphone echo measurement. This is an important measurement because it is very distracting hearing an echo of your own voice when you're talking to someone.
At the beginning of the sequence, we have the reminder about the bandwidth it's set up for, and we're wideband, so that's good. The echo is actually made by a metric called TCLW. I'll explain that a bit later. And it's normalized by use of the speaker receive level and send levels that we measured previously. They were stored and will now be recalled. In this measurement, you have the option to run a long conditioning cycle, which is 8 sentences going back and forth between sending and receiving direction, alternating male and female. The object here is to make sure that the device is in a stable state.
The jacket hung on the back of the wide chair. The jacket hung on the back of the wide chair.
So delays were measured so that these stimulus signals can be lined up.
The jacket hung on the back of the wide
Sending.
chair.
The coffee stand is
Receiving.
too high for the couch.
A pound of
Sending.
sugar costs more than eggs.
The ship was
Receiving.
torn apart on the sharp reef.
The coffee stand
Sending.
is too high for the couch.
The
Receiving.
jacket hung on the back of the wide chair.
The ship
Sending.
was torn apart on the sharp reef.
A pound
Receiving.
of sugar costs more than
Conditioning
eggs.
is done.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
The jacket hung on the back of the wide chair.
So as in some of the other
Sugar costs more
sequences,
than eggs.
the
coffee
IEEE
stand
speech
is too
segment
high
is
for the
played one
couch.
time for
The
further
ship was torn
conditioning,
apart on
and the
sharp
measurement
reef.
is performed on the second repetition.
The jacket hung on
On
the
the
back
left-hand
of the wide
graph,
chair.
you can see
Pound of
echo
sugar costs
frequency
more than
response
eggs.
with
The
a
coffee
solid
stand
line.
is too
This
high
will be
for the
performed
couch.
3
The
times
ship
at 3
was
different
torn apart
stimulus
on the
levels.
sharp reef.
Echo
The
frequency
jacket hung on the
response
back of the
is
wide
the signal
chair.
coming back
Pound of
from the
sugar
send
costs more than
direction
eggs.
out of the
The
dot
coffee stand is too
relative
high for the
to
couch.
the stimulus
ship
that
was
was
torn
sent to the
apart on the
dot
sharp
in the
reef.
receiving direction.
The jacket hung on the back of the wide chair.
Now, if the
Pound of sugar
device
costs more
was
than
linear
eggs.
and noise-free,
Coffee stand
all of
is
these
too high
frequency
for the
responses would lie on
The
top
ship
of
was
each
torn
other,
apart on the
but
sharp
they do
reef.
not. And in this case, it shows that most of what's being measured here is actually noise.
Coffee stand is too high for the couch.
You really can't see it from the waveform on the right,
Sharp reef.
but there is a little noise that's coming back from the device, and that more or less is contaminating the frequency response, except in this lowest level, in the dotted blue curve. So on the left we have the male information, and on the right it's female. If you look at the frequency response for male echo on the yellow curve and take an eyeball average, you will get approximately minus 70 dB. Change the sign and you get approximately plus 70 dB, which is the TCLW. Similar on the right is the information for female. The box at the bottom shows how the normalization was done. The idea is to correct the measurement to what it would have been if the sending output level and the receiving output level were exactly nominal. Some authorities do not recommend doing this, but it's in the TIA 920 standard. You can choose not to do this if you prefer, or follow the standard and perform the normalization. Now we can also take a look at the waveforms and see if there were any noise bursts of any significance during any of these waveforms. There are some visible, but they're pretty small. So mostly what we're measuring here is noise coming back with an occasional burst, like you see in the lower left graph. That would be the male echo at the lowest level. In a similar way, you can see something on the lower right from the female echo measurement. There's a little blurb around 3 seconds. As before, we can save to an Excel sheet or to the master report. We'll use the master report as before and put any notes here about the conditions or anything else that we've observed during the test. Once we click that, the Excel sheets will be generated, and when that's finished, the sequence is done. And now we are finished.
Now let's look at a different type of measurement. Here we're going to look at a send directionality measurement. This is particularly useful for measuring the acoustic performance of a speakerphone off-axis. Although this was originally used for conference phones, we're seeing renewed interest in this measurement from people using smart speakers as communication devices. In this demo, we manually rotate the phone, although you could further automate this by using a turntable controlled from within SoundCheck.
This is a measurement of send frequency response and level performed at several different angles and then compared to each other. The idea is to see if the phone is well usable over a wide range of angles on the front side. Since the frequency response measurement is the same that you've seen before, we won't actually go through it, but I'll sort of summarize the process here. The first is to set the phone up at 0 degrees and measure send frequency response. If you need to reset the volume control, you can redo that one until the volume control is set properly. Then you'll get a prompt to move the phone to the 30-degree position and measure again, and so forth for the others. After that's done, you will then see the calculations for send directionality. So now we'll skip to the end and look at that. When the measurements are done, you'll see a set of frequency response curves like the one on the upper right. All 5 positions frequency responses are on the same graph, and you can see pretty easily that they're not that different from each other. The solid line is the 0-degree reference. From those response measurements, the overall level is calculated. That's shown in the upper left box. There is a little tolerance of plus minus a few dB, and the difference that you see, send level directionality, is the difference in level between that particular angle and the reference. You can see they're all pretty small, so all 4 pass, and the entire test is passed. It means that the sending response and level from the front side of the phone is about the same at all these various angles. At the end, you can save the data to a simple Excel sheet or to the test report, just as we've done for the other sequences. After that is complete, then the sequence is finished.
Moving on, we have one more demo from the suite of test sequences. Here we're going to look at receive noise and single frequency interference. This tells us how much noise is present in the communication device during a call.
First, check the bandwidth setup. These measurements should be made with volume controls set to nominal. If you don't know where that is, you can perform measurements and find out. There's a conditioning signal before the noise measurement. Minus 20 dBu is the default.
The jacket hung on the back of the
Now there will
wide
be a full chain of
sugar costs more
IEEE
than
speech
eggs.
sentences
The
played
coffee stand
for
is too
conditioning
high for the couch.
to get the device in
The
a
ship
stable
was torn
state.
apart
And
on
then
the
one
sharp
more
reef.
sentence.
The jacket hung on the back of the wide chair.
And immediately after this sentence, the noise will be measured. The box in the middle has the measured metrics. Received noise, 23 dBA, is well below the tolerance. Single frequency interference, such as what you see around 600 and 700 hertz, is low, and it's low enough that it passes the requirement. In the graph, you can see that the white line and the red line are a spectrum, the white being transient noise, that is just right after that last speech stops, and the red is steady state, which is a longer period after a pause of 5 seconds. They both are passing the requirement. In the waveform, the red is the steady state noise, the white is the transient noise near the end of the conditioning signal. So, as before, we can save to a simple Excel sheet or save to the test report, which is what we'll do now. Again, we can put in comments or remarks about the volume control setting or anything else that will help you understand the test after it's over. And when the Excel sheets are written, the sequence will be done.
So that's all the TIA 920 tests we have time for, as I want to make sure we show you some of the other telecom tests too. As you can see, there are many more tests included in this package, and we'd be happy to arrange a demonstration if you want to take a closer look. Next, we're going to talk a little about TIA 5050. This standard establishes receive volume control requirements and testing methods for wireless handset telephones that support narrowband or wideband audio interfaces. Over to you, John.
This is a performance spec that's designed to test the receiving characteristic of a mobile phone to see if there's enough undistorted output to be used in various practical situations. It's designed to be used with an air interface, which is a device to which you place a call with the phone under test, and the signals going into the phone are provided to the air interface. The sequence has calibration sequence for that air interface as well as for the hat's ear. You can also see that it uses a positioning device which helps put the phone in the correct place and at the right force. In a moment, I'll show you a little bit more about how that works. In the measurements you're going to see today, the connection is not to an air interface because this lab does not have one, but it's connected to an application on the computer. This means that there's a little bit more in the test than just the cell phone. It's almost like testing a phone back to back. So the performance that you see here is probably a little bit worse than the phone itself had we tested it on an air interface as intended. Nevertheless, I think you'll see exactly how the sequence works. I will walk you through that. So to sum up, the sequence will show if the receiving performance of a cell phone is sufficiently loud and sufficiently undistorted for practical use according to the standard TIA 5050. The first thing we need to do is to say what the bandwidth of our phone is. This is a narrowband phone, so that's what we pick. The next prompt tells you how to navigate the sequence. The standard requires measurements that include frequency response, conversational gain, and distortion to be performed both at 2 newtons and 8 newtons pressure on the handset. They can be performed in any order, but it's usually better to start with 2 newtons. The positioner may work better that way. If you need to repeat any one of the sets, you can do so. Now we make sure the handset is set for 2 newtons pressure force and that the call is actually active.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
You just heard the IEEE male speech as the test signal. So when we look at these first results, we need to find out if the conversational gain and the frequency response are okay. If you look in the box we just highlighted, you can see conversational gain is fine, but frequency response is not. The free field frequency response, upper left, doesn't pass, although it's close, and neither does the diffuse field frequency response. Again, it's close. When we look at the waveforms in the lower left, we can see 4 sentences clearly, so the measurement appears to be valid. In this case, we go on to the final test, which is distortion. For distortion, we have 2 conditioning signals to keep the phone active during the test. The first one is a sentence, and the second one is a syllable called ba that actually is repeated in front of each noise burst. You'll hear this in a moment.
The jacket hung on the back of the wide chair. Back, 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 back.
If you look at the upper right graph, you'll see the waveforms of the test. The upper left graph shows the spectrum. What you see now is very typical. Something looks like a rectangle at the test frequency. Back to the waveform graph on the upper right. The signal up to 2.6 seconds is the sentence conditioning. It's not measured. It's merely made to keep the device active. The burst around 2.8 seconds is the short conditioning. It's to keep the device active during the measurement. The noise signal, centered around 3 seconds, is the part that's actually measured. And that sequence of pulses goes on for 10 times. As the test progresses, in the lower left-hand graph, you can see 2 curves. The yellow curve is the signal-to-noise and distortion ratio. It's actually a signal-to-garbage ratio. The green curve above it is measured in a similar way, but it only includes second and third harmonics. So it's just the distortion part, not the noise part. The middle lower graph shows distortion in percentage terms. That might be a bit more familiar. When we look at the distortion results, we could see from the box that the signal-to-noise and distortion test did not pass, especially between 1 and 2 kilohertz. If we look at some of the other boxes, we can get some information. The lower left, which is level versus frequency, appears normal. The upper right, which is signal-to-distortion ratio, is much better than signal-to-distortion and noise ratio. This tells us that most of the garbage in the test was noise, not so much distortion. Now we can go and look at the waveforms for each of those frequencies. The purpose of this is to see if the phone remained active during all of the tests. And at first glance, that seems to be generally the case. You can see the sentence activation, you can see the short activation, and the noise burst. So this appears okay. Now we don't need to go see those curves. Let's measure again at 8 newtons. So here we'll go and actually change the force on the handset, moving it inward for an application force of 8 newtons. You might hear a little noise as the positioner is being changed. The volume control has not been changed from the position it was in before.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
So this test is exactly what was happening with 2 newtons. And so again, if we look at the conversational gain, we can see in this case it did not pass. So we need to make a change in the volume control setting and see if there is a volume control position that will allow this test to pass. We'll go ahead and do that and then measure again. We can keep doing this
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
We can keep going in this loop until we get the volume control setting to our satisfaction. In this case, we've got a setting that does allow the conversational gain to pass. But the frequency response, once again, does not. It seems to be a valid measurement, so we're going on to the distortion.
The jacket hung on the back of the wide chair. Bap, 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 bap.
In the lower right box, you can see the frequency that has been tested and is showing on the graph, and the application force. If you look again at the upper left graph, you'll see this rectangular shape, which is normal when the test is being performed at a specific frequency.
The jacket hung on the back of the wide chair.
So far, the signal to distortion and noise ratio, the yellow curve in the lower left, is above the 20 dB requirement. But now it dips below. And if you look carefully at the spectrum in the upper left, you may be able to see that there's more noise in there than there was before. In a similar way, at 1.6 kilohertz, there's more noise in the measurement than there was before. This is noise generated by the device.
The jacket hung on the back of the wide chair.
Remember that the noise we put into the device should look like a rectangle. Anything else represents some kind of distortion that the device has done. So let's look at these results before we go further. The signal to noise and distortion ratio has not passed, again, particularly between 1 and 2 kilohertz. Once again, if we look at the other graphs, we may get a clue as to what's going on. The signal to distortion ratio, which does not include the noise, is at quite a bit higher. This tells us that the garbage that's produced is mostly noise, just like before. So we have the measurements done at both application forces. Now we can look at the summary. Before we decide how to save the data, just look at the screen. The left side is all of the information for 8 newtons. The right side is the information for 2 newtons. On the left side, we can see that the conversational gain is passed, but not the signal to distortion and noise, and not frequency response. Similarly, on the right, the conversational gain is fine for 2 newtons, but the frequency response and distortion are not. Now, I'll choose not to save raw data to an Excel sheet. Instead, I'd like us to save data to a master report that goes into a particular format. We can include that word demo in the name of the file, and we can write some notes that will go into the Excel sheet to say anything special that occurred during this test, maybe the volume control positionings. So there's been a little interaction between SoundCheck and Excel, and the test report has been saved.
Now let's demonstrate double talk. Double talk occurs when 2 people talk on the phone at the same time. A communications device needs to be able to handle this without clipping or cutting off one person's speech or making other unwelcome sounds. There are both ITU and ETSI standards that measure how the device behaves in this situation, and John is going to talk about these. This test sequence has taken a long time to develop, as we had to add some functionality into SoundCheck to enable John to write it. The silent stimulus step, RMS level versus time, and a histogram post-processing step were all added in SoundCheck 20 specifically for these type of communications tests. Anyway, let's take a look.
First, let's just say what double talk is. It occurs when 2 people are having a conversation, and either accidentally or on purpose, one person tries to talk while the other is still talking. Now, that can happen accidentally, or it can happen on purpose if somebody needs to interrupt. But a device needs to be able to handle that without clipping off the other person's speech or making other nasty sounds. And so that's what the test is intended to reveal. I'll show you how that is intended to be measured with the following slide. The sequence implements two Doubletalk standards. First one is from ITU-T P502. It basically is a method that was originally made for an artificial speech, but it's been adapted for use with real speech. The result is one parameter for the entire test. It's something called the attenuation range, which is obtained by statistical methods. The attenuation range is basically how much loss there is when signals are going both ways at the same time. And that AH is classified according to P.340. You'll see the look of that in the sequence as it runs. The other standard implemented is ETSI TS126-132. It takes a little different approach. It does use real speech, but the result is classified as percent of time in several behavior categories. There's full duplex, there's clipping in 3 different time lengths, and there's echo in 3 different time lengths. Fortunately, there are some items in common with these two standards. First of all, they use the same test signal from P.501. They also use the same conditioning signals from P.501. And they use level versus time differences, which I'll explain in the next slide. The result of these common items is that one measurement can be used to implement both standards. Now, speech levels versus time, what does that look like? The speech waveform
The jacket hung on the back of the wide
is
chair.
indicated in gray. The level versus time is shown in yellow. You might say it's smoothed out. That's technically not totally true, but it is one way of looking at it. And the amount of smoothing depends on the time constant. Actually, in the standards, there are 2 different time constants in use, which the sequence implements. So, how do Doubletalk measurements work using level differences? It begins by playing speech from a mouth simulator into a device where the Doubletalk signal is played by itself and the level versus time is taken. Then the Doubletalk signal is played again, this time with the SingleTalk signal that's going in the opposite direction is present, and the level versus time again is measured. And there could be some differences between that and the first measurement, and that is shown in the difference. And so anything that is a positive difference indicates an echo that actually is audible, and the levels that are below indicate some kind of clipping or level loss. And if it's only brief, you may not notice it, but if it's long enough, it'll actually tell you that speech is being missed, perhaps even entire words. For this demonstration, we'll be testing a small USB speakerphone, and we'll use a standard mouth simulator. There's also a small microphone placed right at the acoustical opening of the speakerphone. That's used to synchronize the signals from the mouth with the sound as it comes out of the speakerphone. You'll see how that works when the sequence runs. The setup here is a fairly standard arrangement where the mouth is 50 centimeters from the device under test. When the sequence begins, you'll be given an opportunity to set some of the test parameters. The most important ones are the sending level from the mouth and the receiving level from the device under test. The defaults that will be shown here are pretty typical, and they will test the device under favorable conditions. But by changing those levels, you can test the device under less than favorable conditions where it may struggle a bit to provide full duplex operation. So when the sequence does start, you'll be given a prompt just to remind you about the setup, the positions that we showed you earlier. The sending level is pretty typical, but again, it can vary over a wide range. Also, the receiving level is typical, but it can also vary quite a bit. You'll also get a chance to put in a 100 Hz high-pass filter that's a good idea to eliminate noise that might otherwise be part of the measurement. And now we start.
The jacket hung on the back of the wide chair. The jacket hung on the back of the wide chair. The jacket hung on the back of the wide chair. The jacket hung on the back of the wide chair. The jacket hung on the back of the wide chair.
Grace.
Port is a strong wine with a smoky taste.
A pencil with black lead writes best. The shaky barn fell with a loud crash. The lamp shone with a steady green flame. They took the axe and saw to the forest.
The glow deepened in the eyes of the sweet girl. Pluck the bright rose without leaves. Clothes and lodging are free to new men. A cramp is no small danger on a swim.
5 5 5
5 5 5 5
5
The shaky barn fell with a loud crash.
Pluck the bright rose without leaves.
A pencil with black lead writes best.
The glow deepened in the eyes of the sweet girl.
Grace.
Port is a strong wine with a smoky taste.
A pencil with black lead writes best. The shaky barn fell with a loud crash. The lamp shone with a steady green flame. They took the axe and saw to the forest.
The glow deepened in the eyes of the sweet girl. Pluck the bright rose without leaves. Clothes and lodging are free to new men. A cramp is no small danger on a swim.
The last switch cannot be turned off.
5
It's easy to tell the depth of a well.
5
4 hours of steady
5
work faced us.
5
We frown when events take a bad turn.
5
Rice is often served in round bowls.
5
The hogs were fed chopped
5
corn and garbage.
Jazz and
5
swing fans like fast music.
The juice of lemons makes
The
fine
shaky
punch.
barn fell with a loud crash.
To the dark blue
Pluck the bright rose without
He knew the
leaves.
skill of the great young
A pencil with black lead writes
These days,
best.
a chicken leg
The
is a
glow
rare
deepened
dish.
in the eyes
A
of the
large
sweet
size
girl.
in stockings is hard to sell.
Now that the signals have been played back and recorded, the sequence will do post-processing to get level versus time curves, and then do the statistical operations to get the attenuation range to implement the first standard. The yellow curve is level versus time for the period when both signals are going on at the same time. The gray areas are the areas defined as double talk. At this point, the sequence is calculating in a different way to implement the TS-126-132 standard. You can see the waveforms here, along with some areas that are being looked at in different ways. The yellow curve, again, is level versus time. The gray areas are defined as double talk. The red areas are defined as single talk. In the upper left box, you can see that the first part of the series, where there are words only, the word 5, is given 96.4% full duplex. The second part, which is full words, or sentences, is 95.6%. The next part is to calculate what goes on during the single talk portions. You may notice that there are some spikes of the yellow curve that extend above 0. Those are echoes that don't happen for very long, but they may be audible, and the sequence will evaluate that. There is also some attenuation in the single talk area, which may not be a bad thing. If you look in the second to the upper right box, you can see that there is not much activity in categories E, F, and G, but that is echo, which might be audible. That applies to the section where single words are spoken. That is the left-hand part of the curve. And now the same calculations are going to be applied to the right-hand part of the curve. And that shows, again, in levels E, F, and G, that there is some echo, but it might be enough to be audible. Double talk behavior is complicated, but the sequence offers numerical values that you can use to benchmark the behavior of a device as you're developing it. You can also dig a little bit deeper in the sequence and get some idea of why a device is doing what it's doing. The sequence is applicable to headsets, where double talk is sometimes an issue, but it's mostly applicable to speakerphones or any device with a speakerphone-like function, where two people are talking in real time back and forth and expect to be able to have a duplex conversation. You can use the sequence with hats or with a standard mouth simulator and a microphone. There's also supporting sequences to do calibration and also to set the volume controls on the device.
Finally, we'll close with a different type of communications measurement. Polka is a fast and cost-effective alternative to a panel of human listeners for perceptual measurements of speech degradation from telephones to smart devices. It uses a perceptual algorithm to compare the degraded signal to the corresponding reference signal. This determines the mean opinion score, or MOS, in an end-to-end test. It has many applications across all types of communication devices. For example, assessing the impact of noise reduction algorithms, evaluating Bluetooth degradation due to packet loss, or analyzing distortions introduced into the audio path. This is a new option in SoundCheck, and it can be added to any system, version 20 or later. Let me hand over to my colleague Les to give you a quick demo of how this works.
Thank you, Steve. Our Polka option fully integrates Opticom's Polka version 3 algorithm as specified in the ITU-T P863 standard directly into SoundCheck. It operates just like any other post-processing step within SoundCheck. You can configure the reference and response waveforms, set test parameters, and define outputs through the familiar SoundCheck interface. The Polka algorithm is called from within SoundCheck and returns results as graphs and tables like any other analysis. It can, of course, be used within sequences to accelerate and simplify test procedures, and can also be used to process imported data using batch file processing. Polka is a valuable addition to anyone testing speech quality in communications devices. Some common applications of this test might include assessing the impact of a noise reduction algorithm on an audio communication system, evaluating the perceived audio degradation in a Bluetooth connection due to packet loss, analyzing distortions introduced in the audio path, quantifying the impact of various speech codecs on perceived speech quality. Let's look at a few possible Polka setups. Here is an example of a setup we can use for characterizing the perceived audio degradation in a Bluetooth connection due to packet loss. The mouth simulator plays back a reference wave file that is recorded through the Bluetooth microphone. The recorded degraded response is compared to the original reference wave file, and the mean opinion score, or MOS, is returned. Here's an example of another possible Polka test. In this setup, an end-to-end call can be established. For example, a call can be made to a conference phone, which is the device under test. The signal on the receiving end is recorded and analyzed for speech quality. Let's look at a simple Polka SoundCheck sequence. This sequence is similar to the conference phone setup I just displayed. This sequence uses the batch processing capability introduced into SoundCheck 20 to access pairs of WAV files for Polka analysis. These WAV files are temporarily loaded into the memory list and passed through the Polka post-processing step for analysis. This loop recalls and analyzes 4 sets of WAV files and reports the Polka mean opinion score on a scale of 1 to 5, 1 being poor, 5 being best, and a score of around 4 considered very good. The advantage of batch processing is that I can conceivably test hundreds or thousands of pairs of WAV files without loading all the files into a sequence at once, efficiently managing the sequence size, memory, and performance. Let's look at the Polka post-processing step. The step compares the recalled reference and response files. The drop list allows you to select the measurement type, acoustic, digital, or voltage. This drop list shows the operating modes, options including full band, narrow band, and super wideband, including the latest version 3 algorithm. But it also supports Opticom version 2.4 if you need to correlate results with a lab that uses the legacy 2.4 algorithm. In addition to the MOS, we can choose additional outputs including ASR, attenuation, delay, MOS per frame, pitch, R factor, and SNR. Since the sequence is using recall WAV files, you won't hear the speech files when I run the sequence, but I'll play back the reference WAV file through my signal generator so you can hear what's being analyzed.
The shaky barn fell with a loud crash.
Clothes and lodging are free to new men.
I'll run the sequence and note the highlighted steps in the sequence editor, particularly through the loop, which will run 4 times before the final display steps. There are 2 tabs in my display step. As you watch the sequence run, this display step showed the active iteration of the 4 WAV files being analyzed. The top display showed the reference WAV file, and the bottom displayed the reference WAV file along with the response file superimposed. In the second display step, we see the mean opinion scores, or MOS, of the 4 WAV files and additional outputs below. These are displayed in tables, and we can see the MOS score are 3.4, 3.98, 3.4, and 3.98. As you can see, SoundCheck's integration of Polka is fast and easy, and an essential addition for characterizing speech quality.
Thank you, Les. And thank you, John, for your demos earlier. I just want to leave you with a couple of thoughts. First, although this seminar has been focused on our pre-written test sequences for communication devices, you can of course program your own test sequences for communications or any other application too. All the features in these tests are available to use exactly how you want, and many people prefer to devise their own test if they don't need to measure to standards. Second, SoundCheck is not just for communications test. It can be used to implement pretty much any audio test that you can imagine. We've got almost 30 years experience testing all kinds of devices, ranging from simple transducers to smart devices, hearing aids, and more. So its applications go way beyond testing just a finished communications device. You can use it along the way to evaluate components, measure subassemblies, test the effectiveness of algorithms, and more. It can even be used on a production line for final assembly testing. That's all we have time to show you today. Hopefully this has given you a good overview of our communication standards test packages for SoundCheck. If you want a more detailed demonstration or want to see something that we did not show, please give us a shout. Thank you.